Okay. Good morning, students. So today we have lecture number 6. Lecture number 6 on fluid mechanics. Fluid mechanics. You see first year. Okay. So fluid mechanics. So we have started fluid mechanics. Okay. So in the previous class we have studied about the Bernoulli's theorem. Bernoulli's theorem. So from that Bernoulli's theorem, that is it states or it relates the energy of the flowing fluid. Energy of flowing fluid is related by the equation called Bernoulli's equation or Bernoulli's theorem. So now the last part, in the previous class only I told the last meaning. The meaning of that equation is that finally when height is taken as constant, the meaning of that equation was that when the velocity of fluid is larger, if velocity of fluid is larger, the pressure at that point will be less. If the velocity of the fluid is less, the pressure at that point will be more. So that is the meaning. So depending upon that meaning, so we have some applications of Bernoulli's theorem. Applications of Bernoulli's theorem. Okay. So some applications of Bernoulli's theorem we have to study. Okay. So first one, if we blow the air on a sheet of paper, if we blow the air on the surface of sheet of paper, it is observed that the paper will rise up. That is, this is a paper. I will hold this paper like this. So if we blow air above this sheet of paper, so we observe that the sheet of paper will rise up. The sheet of paper will rise up. This is because when we blow the air, the velocity of air is very larger on the upper surface of the paper, and velocity of air below the paper will be less. So here velocity of air is very larger, so pressure here will decreases. Pressure on the upper surface of the paper will decreases, whereas pressure below the paper is more. So as a result, a upward force acts on this paper, so the paper will move upwards. See here, if we blow the air, the paper will move up. This is one of the application of Bernoulli's theorem. You observe, this is happening because when we blow the air, the velocity of air is very larger. So velocity of air is larger, the pressure will decreases, and below the paper velocity of air is less, so pressure will be more. So net pressure will be upward, so net force acts on the paper in upward direction. As a result, paper will move upward. That is one of the application of Bernoulli's theorem. That is, the paper will move upward because of blowing of air on the surface of the paper, on the upper surface of the paper. So similarly, same way, the aerofoil, that is the wings of an the wings of an aeroplane, the wings of an aeroplane, the aerofoil, that is dynamic lift, or I will call it as a dynamic lift of wings of aeroplane. Dynamic lift. Okay. The wings of an aeroplane are given a specific design. The wings of aeroplane are given a specific design. That is, the upper surface is convex. The upper surface is convex and lower surface is concave. The upper surface is convex and lower surface is concave. As a result of that, the air blows. So when the aeroplane, this is a wing of an aeroplane, just roughly I am drawing, the upper surface is made more convex and lower surface is concave. Like this shape is given to the aeroplane. Slightly concave, not much more, slightly concave. So now when air blows when air blows, that is when the aeroplane moves forward, this is the direction of motion of aeroplane. When the aeroplane moves forward, the air blows on the upper surface of the wing with larger velocity. The velocity of air on the upper surface of aerofoil is large. The velocity of air on the upper surface of the aerofoil is large, and here velocity of air or speed of air is less. Speed of air is less. As a result of this, the velocity of air is larger. The pressure at the upper surface of the aerofoil, will be less, and here velocity, the speed of air is less, so pressure at the below the wing, that is aerofoil, the pressure will be more. So here pressure is more, here pressure is less. As a result, a net pressure acts in the upward direction. As a result, the wings of an aeroplane will experience as a upward force, and that upward force we called as dynamic lift. That dynamic lift or upward force is given by the formula net pressure, that is pressure difference. You can say pressure difference into area of wing, So that is pressure difference. Here pressure is less, here pressure is more. The pressure difference between these 2 points we have to take, that is the net pressure into area of the wing will give the upward force acting on this wing. As a result, the aeroplane is lifted up, so it will help the aeroplane to move upward. Understood? So this is also on the basis of Bernoulli's theorem. That is, here velocity of the air is larger, so pressure decreases, and here velocity of air is less, so pressure increases. As a result, a pressure difference is created on the upper surface and lower surface of the aerofoil. As a result of that, a net pressure or net force acts in the upward direction. So the wings of an aeroplane will experience dynamic lift, upward force, so that you can calculate. This also numerical is also there on this, so that dynamic lift or upward force acting on that is given by difference in the pressure into area of the wing. That will give the net upward force acting on the wing, on one wing. Understood? So this will help the aeroplane to move upward. Understood? So this is one of the application of Bernoulli's theorem. Okay, next working of atomizer or sprayer. Sprayer, scent bottle, you will use in the home, that scent bottle, working of a scent bottle, or you can say, okay. Okay, here this scent bottle. So this is a tube, a very thin tube, vertical tube immersed in the liquid or fluid which has to be sprayed. Okay. So this is another tube, another small tube, horizontal tube, and this is a piston. Just for your understanding, I am drawing all these things like this. So this is small nozzle or small hole is there. So from where the liquid is sprayed into the small droplets. Okay. So now here inside this bottle or here the pressure is very large. So the pressure is very large. So that is pressure of the liquid. The liquid is at a height. So therefore there will be a pressure. So pressure. Here pressure is large, and now when this piston moves forward, when this piston moves forward with then a large air, that is the wind of air is created. A large velocity air is created in this horizontal tube. As a result of that, the velocity of the air will be very large. The velocity of air will be very large here. So when the velocity of air is very large, the pressure at this point will decreases. The pressure at this point will decreases, and pressure here is more. So here pressure is more, here pressure is less. So the fluid will move upward. A fluid moves from higher pressure region to lower pressure region, or a liquid moves. Remember that a liquid moves, liquid or fluid moves from higher pressure region to lower pressure region. A liquid moves from higher pressure region to lower pressure region. Here pressure is high and here pressure is low. As a result, the liquid will move up in the vertical tube. The liquid will move upward in the vertical tube, and when it gets mixed with the wind, that is air, so it spread into the small droplets. It breaks up, the liquid breaks up and it spreads into the small droplets. So this is working of atomizer or sprayer. The main concept is that here a large velocity air is created. A large velocity air is created by moving the piston, or you can, some of the books also you can tell like this. A balloon is connected. Here a balloon is connected. A balloon is connected. When the balloon is blown, the large velocity wind, air is created. So that velocity of the air will be larger at this top surface of this tube. So the pressure at this point will be less and pressure at this point will be more. So therefore the liquid will move from higher pressure region to lower pressure region, that is liquid will move upward in the vertical tube, and then it gets mixed with the air, then it spreads in the small droplets. So this is the working of atomizer or sprayer. Understood? It is also on the basis of Bernoulli's theorem. It is also on the basis of Bernoulli's theorem. Next application. Next application, third one. No, fourth one. So blowing off roofs. Blowing off roofs by wind. Okay. So a roof, that is a tin shed, your home is there. So now tin roof, that is the roof is made up of very thin metal plates. So now inside this home, the velocity of the air is less. Velocity of air is less. And outside the home, that is on the upper surface of the home, so during the hurricane or during the storm, a large velocity air will move. Large velocity air will flows. So on the upper surface of the home, that is on the upper surface of the roof, tin shed. So now here inside the home, the velocity of air is less, so here pressure will be more. Inside the home the pressure will be more, whereas on the top surface of the roof the pressure will be less. Because velocity of air is more. So where velocity is more, there pressure will be less. Where velocity is less, there pressure will be more. So here velocity of air is less, so pressure will be more according to Bernoulli's principle. And here velocity of air is large, so pressure will be less. As a result of that, these plates, thin metallic plates will be there. So these thin metallic plates will experience as a net pressure in the upward direction. That is a net force acts in the upward direction. As a result, they are open. That is, they move slightly upward, and when they move slightly upward, because of the wind, they are blown off. Because of the fast moving wind, that is a high speed wind, so the roofs of the home, the roofs of the house are blown off by the large velocity wind. Understood? So this also by the this is also application of Bernoulli's theorem. Understood? So here once again, during wind, during a hurricane or during storm, a large velocity wind blows over the surface of the roof, blows over the surface of the roof. So as a result of that, the velocity of air will be larger and pressure will be less on the upper surface of the roof. Whereas inside the home, that is below the roof, the velocity of this is wall, so velocity of air here is less. Velocity of air inside the home will be less, and the pressure inside the home will be more, and pressure above the roof is less. As a result, a net pressure acts on the roof in the upward direction. So the roof gets lifted up by a slight distance, and when it lifted up by a small distance, and a fast moving wind, that is wind, very high velocity wind, blows the roof from the home. Understood? So this is application based on the Bernoulli's theorem only. Understood? So next another application, Magnus Effect. Magnus Effect. Okay. This is fifth one. Okay. A ping pong ball, a spinning ball thrown into the air will change its path of motion. A ping pong ball or a spinning ball, when it is thrown with a high velocity in the air, it will change its direction of motion. In which direction it has to move? In that direction it does not move, it will change the direction of motion. That is also due to the change in the velocity. So when a ball, spinning ball is moving, when a spinning ball is moving inside the air, in a air medium, so the air flows. The velocity of the air above the ball will be larger. The velocity of the air above the ball will be larger, whereas the velocity of the air below the ball will be smaller. Velocity of air will be smaller. Velocity of air or speed of air will be larger. So velocity is larger, as a result pressure will be less, and here velocity of air is small. Velocity of air is small. This is large, this is small. So as a result pressure will be more. So hence the ball will experience a upward force or upward lift, hence it will change its direction. That is, actually it has to fall here. But it will move here. This another path. It will follow the another path. It will fall here. Understood? See here, when a ping pong ball is thrown with very high velocity, with very speed, so we observe that after traveling a certain distance, the ball will change its direction. You can see in our daily life also. Appan jatrage sigtav ball, plastic ball. So when that ball moves with very large velocity in the air medium, that ball will change its direction of motion. It will change its direction of motion, or it will change its path. So this effect is called as Magnus Effect. This effect is called as Magnus Effect, and it is also due to the application. This is also application of Bernoulli's theorem. It's simple. So here velocity of the air is larger, so pressure is less. Here the velocity of air is smaller, so pressure is more. As a result, a net pressure acts in the upward direction, a net force acts in the upward direction, hence the ball will take another path. It will take another path, or it will just change the path of motion. And this effect is called as a Magnus Effect. This effect is called as a Magnus Effect. Understood? So these are some applications of Bernoulli's theorem. Understood? Okay. So now next application. So we shall study the next application of this Bernoulli's theorem. That is 7th one, I think. Venturimeter. Venturimeter. Okay. It's all simple. So I will explain in a simple way. So Venturimeter. Venturimeter is a device which works on the principle of Bernoulli's theorem. Venturimeter is a device which works on the principle of Bernoulli's theorem, and it is used to measure the rate of flow of liquid through a pipe. It is used to measure the rate of flow of liquid through a pipe. That is, the volume of liquid flowing per second can be measured. How much volume of liquid is flowing per second, that can be measured with the help of Venturimeter. So Venturimeter is a device which works on the principle of Bernoulli's theorem, and it is a device used to measure the rate of flow of liquid through a tube. Okay. So this is a Venturimeter consists of two narrow tubes, two larger tubes. I will say this one as tube A and this one has tube C, this one is tube B. Okay, this is tube A, this is tube C, and this is tube B. Okay. A Venturimeter is a device which works on the principle of Bernoulli's theorem. It is used to measure the rate of flow of liquids through this tube. And now when the liquid flows through this tube, the volume of liquid flowing per second can be measured. The volume of liquid flowing per second can be measured. So here, two more tubes, that is two vertical tubes are connected. Two vertical tubes D and E. Let's say this is one vertical tube connected to the tube A, and another vertical tube connected to the smaller tube B. Okay. This is vertical tube, another vertical tube. This one is D, this one is E. Okay. So now, say a Venturimeter consists of two larger tubes A and C and connected with a narrow tube B. This A and C are connected with a narrow tube B, and two vertical tubes D and E are inserted to measure the pressure. So this will give the pressure. Okay. So here this area, the area of this tube is A1 and area of the tube, cross-sectional area of the tube B as A2. Area of the tube A is A1, small a1, and area of the tube B is A2. Okay. Pressure at this point is P1. Pressure in the larger tube is P1 and pressure in this smaller tube B is P2. Velocity of liquid here is V1 and here velocity of liquid is V2. Velocity of liquid in the larger tube A is V1 and area of cross section of this tube is A1 and pressure at this point, that is pressure in this tube, is P1, and here the velocity of liquid is V2, the area of cross section is A2 and pressure is P2. So that is, here the velocity of the liquid will be less. Here the velocity of the liquid will be less because the width, that is the area of cross section of the tube, is more. So the pressure P1 will be less. So this height of the liquid will be less, and here the velocity of the liquid is more. Here the velocity of the liquid is more. So here pressure will be here velocity of the liquid is more, so here pressure P2 will be less, pressure P2 will be less, here velocity of the liquid is less, so pressure P1 will be more, pressure P1 will be more. So here P1 will be more and here pressure, this will be less. So this will indicate the pressure, it will indicate the pressure, and this difference, that is a difference in the liquid level inside these vertical tubes. Okay, difference in the liquid level inside the vertical tubes will give the pressure difference, will give the pressure difference. Difference in the height of the liquid in the vertical tubes will give the pressure difference. Here pressure is more because velocity of the liquid is less, here velocity of the liquid is more, so pressure is less. So here the height of the liquid will be less and here height of the liquid is more, so the difference in the height of the liquid will give the pressure difference, that is P1 minus P2. P1 minus P2 is equal to rho GH. P1 minus P2 is equal to rho GH. P1 is pressure in this tube A or C and P2 is pressure in the tube, narrow tube B, and that is equal to rho. Then density, rho is the density of the liquid, G acceleration due to gravity, H is the difference in the height of the liquid in the vertical tubes. Understood? So now when the liquid flows, in these tubes, so here the velocity of the liquid will be more and here the velocity of the liquid will be less. So now apply the Bernoulli's principle here and here. So and let us take this as a same horizontal height. This is at a same horizontal height, that is the both the point, this point as well as this point, both the point are at the same height from the ground level. From the ground level the height, not the height, this H is different, this H, that is height from the ground level or reference level is same, that is this point B and point A are at the same height. So that is the pressure at this point, that is pressure P1, pressure head plus that is potential head, that is height is same here, so they not required, so that one is not required. So that is velocity head. Velocity head you can write it as 1 by 2 rho V1 square, 1 by 2 rho V1 square is equal to, so pressure head at this point, so pressure at that point is P2, pressure head at that point is P2 and plus height is same, height from the reference level is same, so therefore potential head is neglected. Potential head, if you write that potential head here also and here also, in both the terms left hand side, right hand side, it will be same, it will cancel even if you write. So okay, not required. So we will taking this height as same from the reference level. Understood? Because this tube is horizontal tube. Okay, and P2 is pressure at the point B, that is pressure at this point. So plus velocity head, velocity here is different, so here velocity is different, so here velocity head, it is 1 by 2 rho V2 square, 1 by 2 rho V2 square. Understood? So now take that P to this side. So this is by applying Bernoulli's equation, to this point and this point, to this point B and to the point A. So then you will get this equation, that is P1 minus P2 is equal to 1 by 2 rho V2 square minus V1 square, V2 square minus V1 square. Call this as equation number 1. So from equation 1 you can write P1 minus P2 as rho GH is equal to 1 by 2 rho V2 square minus V1 square. Understood? So now further, so we know that equation of continuity, yesterday I told equation of continuity, A1 V1 is equal to A2 V2, and that is equal to, that will give the volume of liquid flowing per unit time. volume of liquid flowing per unit time, that is T is equal to 1 second. T is equal to 1 second. So it is the volume of liquid flowing per second is, I will say it as V. The volume of liquid flowing per second, that is nothing but mass flux. Yesterday, you remember in the previous class, we have written mass flux. It is mass of the liquid flowing per time, mass of the liquid flowing per unit time, that we have written. That same, you will get mass flux. Similarly, volume flux, that is volume of the liquid flowing per unit time. Volume of the liquid flowing per unit time, that is capital V. So let V be the volume of the liquid flowing per unit time. That is A1 V1 is equal to A2 V2 is equal to capital V. Then you can write separately V2 is equal to capital V divided by A2. V2 is equal to capital V divided by A2, and separately V1 is equal to, this is small v1, this is capital V. See the difference between small v and capital V. Small v refers to the velocity, capital V refers to the volume of liquid flowing per second in this. So V1 is equal to capital V divided by A1. Now substitute these two values here. Substitute that two values over there. So I will get GH is equal to, rho cancel, GH is equal to 1 by 2 V2 square. So V2 square, so V2 means capital V divided by A2, it is V square divided by A2 square, minus V1 square, it is capital V square divided by A1 square. Understood this equation? Okay. So now take this V square common, take this V square common, so you will get it is GH is equal to 1 by 2, V square is taken common, so you will get 1 by A2 square minus 1 by A1 square, right. So therefore V square is equal to 2GH divided by, so now cross multiply this one, A1 square minus A2 square divided by A1 square into A2 square. When it is taken to this side, so A1 square into A2 square goes to numerator. So A1 square minus A2 square comes in the denominator. Understand the mathematics? So V square is equal to 2GH A1 square A2 square divided by A1 square minus A2 square, that is V is equal to under root, so A1 A2 I will take outside, so under root 2GH divided by A1 square minus A2 square. So this will give the volume of liquid flowing per second, through this tube. This is called Ventimeter. Ventimeter is nothing but a device used to measure the volume of liquid flowing per second, and capital V is the volume of liquid flowing per second, and A1 and A2 are, A1 is cross sectional area at the point A, A2 is cross sectional area at the point B, and 2GH, H will give the pressure difference, or instead of this formula you can also write like this, the pressure difference, that is capital V is equal to A1 A2 under root 2G divided by, that is A1 square minus A2 square, 2 into GH. Instead of GH we can write it as pressure difference. We want pressure difference in this, that pressure difference is P1 minus P2. Like this also you can write. You can also write like this. It is pressure difference between these two vertical tubes. This GH will give the pressure difference between the vertical tubes. So this is called volume of liquid flowing per second. This is the formula for volume of liquid flowing per second, and this is Ventimeter. Understood? Hope you understood all these things. This much of derivation, all the things are not required. Only just if you write Ventimeter, the application of Bernoulli's theorem I am talking. All these so much they will not ask in the exam. So what they will ask, application of Bernoulli's theorem. Any applications you can write. If you are willing to write, if you want to know more about Ventimeter, so I told maximum. Okay. So these things are useful in the CET classes. how to apply that Bernoulli's theorem to the given situation. We have applied the Bernoulli's theorem to the given situation and we have got the formula for volume of liquid flowing per second, that is rate of flow of liquid. Volume of liquid flowing per second is nothing but rate of flow of liquid through this tube. Rate of flow of liquid through this tube, and rate of flow of liquid through this tube at this point will remain same. Don't get confused. The how much volume of liquid flowing here, that much volume of liquid will flows here per second. The rate of flow of liquid at this point and rate of flow of liquid at this point, at the both the points it will remain same. It does not changes. According to the equation of continuity, in the equation of continuity only I told mass flux at one end is equal to mass flux at the another end. Understood? So rate of volume, rate of flow of liquid will remain same, and therefore in general V is equal to, so you will get this formula, or you can use this formula to get the value. Understood? Okay. So next another one, last application. So this is Ventimeter. Another one application is there. Okay, I will explain that also. Okay. Application of Bernoulli's theorem only. This is also application of Bernoulli's theorem. Velocity of a flux. Velocity of a flux. Okay. Velocity of a flux. So now a container is there. A container is there. In this container, the liquid is filled up to a height capital H. Up to a height capital H from the ground. Up to a height capital H from the ground. A small orifice, a small hole is made at lower end, below the free surface of water. So this is water or liquid of density rho. Liquid of density rho filled up to a height capital H. And now a hole is made. Okay, right? A hole is made at a height, at a depth h below the free surface of water. A hole is made at a depth h, below the free surface of water. As a result of that, the liquid will comes out of this hole. The liquid will comes out of this hole with a velocity. That velocity we call it as velocity of a flux. The velocity with which liquid flows out of a small orifice. The velocity with which liquid flows out of a small orifice is called as velocity of a flux. So now here the cross sectional area of this container, take it as A1, and cross sectional area of this small hole, take it as A2. Pressure here is P1 and pressure here is also P2, not P2, here also P1, because both are exposed to atmosphere. Pressure at this point and pressure at this point will remain same. So now the area of cross section here is A2, area of cross section here is A1, understood? And pressure here is P1 and pressure here is also atmospheric pressure P0, and here also atmospheric pressure P0, because it is also exposed to atmosphere. The hole is made, that hole is exposed to atmosphere, so therefore here pressure is also P0. So now apply Bernoulli's theorem. Apply the Bernoulli's theorem at both the points. So first at here, so pressure head P0 plus pressure head P0, and this height, this level is taken as zero potential level. This hole is at a point where that point is taken as zero potential level. Not, this is not the zero potential level. I am taking this one as the zero potential level, then it becomes simple, easy. So this is pressure head at this point, that at the open end, and plus that is pressure head plus potential head. So potential at this point you can write it as rho GH, because height of the liquid is h from the zero potential level. From the reference level, the height is h, so rho gh plus velocity head 1 by 2 rho v1 square. Here if the velocity of the liquid is v1, if the velocity of the liquid is v1 square is equal to pressure at this point. This is point A and this is point B. Okay. At these 2 points we have to apply the Bernoulli's theorem. Simple. So pressure at this point is P0 plus so potential head, that is pressure head plus potential head. So potential head here is 0 because we have taken it as 0 potential level. So 0 plus velocity head that is 1 by 2 rho v1 square, v1 or v2, v square, v. We have taken velocity of the liquid here as v. So v square. Velocity of the liquid at the orifice is v, so v square. And now we observe that pressure at both the points is same. Pressure at both the points is same because both the ends are exposed to atmosphere, and also the velocity at the open surface, that is at the free end. Since the area is very large, this A1 is very large compared to A2. So V1 is taken to be almost as 0. Since A1 is very large compared to A2, so we can tell V1, that is velocity of the liquid at the open space, that is the liquid will move downward. As the liquid comes out of the container, the liquid level will decrease. That is the velocity of the liquid. Velocity of the liquid at the open end is almost taken as 0. Because this one is very large compared to this small orifice. So that is adjustment we make. So V1 is equal to 0. So therefore, so now what is remaining? Rho GH is equal to, so P0 cancel. So this one also becomes 0. So rho GH is equal to, so what is remaining over there? 1 by 2 rho V square. 1 by 2 rho V square. So rho cancel. So we'll get V square is equal to 2GH, or V is equal to under root 2GH. So this is the expression for velocity of the liquid coming out of the orifice. Velocity of the liquid flowing out of the orifice. So this is called Torricelli law. It is called as also, this is also called as Torricelli law. Torricelli's law. That is the velocity of the liquid coming out of this small orifice is equal to the under root of 2GH. And this velocity of the liquid coming out of this orifice will be same as speed of a object left free, that is free falling body. A body is falling from a height h and it moves through a height h, then the velocity at this point will be also equal to V is equal to under root 2GH. Motion in a straight line. If you study the motion in a straight line, you will understand. If you leave this object from this point, so when it travels a distance h, the velocity of the object will be equal to V is equal to root 2GH. Okay, I will explain that also. Take the formula, V square is equal to U square plus 2GH. You know this formula. This is from the first part. Motion in a straight line, velocity, speed, all that things you will equation of motion. So what is V here? What is V? What is U? What is H? So V is velocity of the body after traveling a distance h. V is velocity of the body after traveling a distance h, and U is velocity of the body before traveling a distance h. Okay, V is velocity of the body after traveling a distance h. U is velocity of the body before traveling a distance h. And now before traveling a distance h, the body was at rest, so U is equal to 0. U is equal to 0. So that is V square is equal to 0 plus 2G and H. So therefore V is equal to under root 2GH. Understood? Directly I written. Actually this formula you will write V square is equal to U square plus 2AS and S is equal to H. Then you will get all these things. Understood? So that is the velocity with which liquid comes out of the small orifice will be equal to the velocity of the object falling freely from the same height as that of the liquid level, from the same height as that of the liquid level. So as it falls, so at this level the velocity of the object is also same as the velocity of the liquid. So this law is called Torricelli law. It is called as Torricelli law. So this is also based on the Bernoulli's theorem. It is also the application of Bernoulli's theorem. Understood? So these all are the some applications of Bernoulli's theorem. Understood? Okay. So in the next class we will study the next concept. This is lecture number 6. In the next class we will study another concepts. Okay.